Hi everybody. In this one we're going to actually start in creating our encryption environment in RSA. In previous video, if you saw it or not, doesn't matter. It just went over the principles of RSA encryption, creating keys. Hopefully you understand that. The function we're looking at here is that we're going to base our generation of keys. First stuff we're going to do is generate keys. Is taking two prime numbers, very large prime numbers, and figuring out what our encryptor, the E exponent, is going to be. So it's going to be, remember, we're going to take E to the, a message to the ETH thing, and then modulo PQ to get our encrypted stuff, and then to get it unencrypted, we're going to take that encrypted value that we just calculated and raise it to the dth power, dth, and do a mod PQ on that to get it unencrypted. So what we need to do is get a set of keys that are going to literally be PQ, and then I'm just highlighting down here E and D. And the PQ E will be our public key, and PQD will be our private key. We'll separate those later. So what we're doing here is we're passing we're assuming that these are prime numbers. You've got them out beforehand, and a lower limit of E, which means, what's the smallest E that we will accept? We want an E that's going to raise that message. We're going to raise the value of ETH to be larger than P times Q, because if it's less than that, all you have to do is take the ETH root of that thing, and then you've decrypted it, and that serves nobody. So this is all this function does. It goes off and finds your phi, your PQ, and then gets a lower limit, which is just basically finding the lowest exponent that would be acceptable that would raise, in this case I'm assuming 2 is going to be the lowest message you'll ever send it, to the ETH that'll be acceptable, that would make that greater than PQ. So with that, what happens, we have the lower limit, and it's literally just a random int that we're going to call, sorry, I was looking at the function. We're going to do find E, which is up here. Find E will take the pH, the phi function, the min E, which is defaulted by 3, but as you see, remember, putting the lower limit in there. It'll find a random int between that min E and the phi function, and it'll just loop through this guy right here until it finds one such that the greatest common divisor between what we're assuming our candidate for E is and phi is not equal 1. So if it equals 1, we found one. That means if it has 1, that means it's inversible, and we can get a D off of that. So that's what's going on here. We come over and get the ETH thing, and then we find the inverse through the inverse function, and then we return PQ, E, and D to our functions. So now we can go to the main function, which is what we're going to use. So we're going to call this my math function here to get this stuff going. And I'll just talk about this particular key generation function for a little bit here. But anyway, we're going to start off by copying our return structure, and then a payload. I'm going to put 1 and 1 in there, and 0. A digit length is how long, it's like a 100-digit prime number or a 100-digit key. And then key bits, how many bits does that number P times Q represent? We're going to create a subfunction called getPrime because I don't want to keep calling it. Anyway, I'm going to go get a getPrime off of P length. P length will be the length in digit numbers, how many, so it's 10 digits, and it'll be a 10-digit prime, and if it's 11, it'll be 11, if it's 1,000, it'll be a 1,000-digit prime. Max attempts is kind of this looping structure we're going to go and ensure that some values are like we want, and it's going to give it basically 10 attempts before it gives up. Number of tests determines how accurate, or not how accurate, but how probabilistic the prime will be. They're all going to be probable primes. In the range we're going to doing 20 tests should be enough. You can certainly make that 50. It's just going to slow it down. And maybe in production we put it up to 50 and just wait for the keys to generate a little bit longer. But I defaulted to 20 because that should work for like a 100-digit prime. Anyway, we get this prime number through this function. I'm going to say plen get prime is my first prime. And then the next thing we're going to do is we want to make sure when we get Q, it's going to be a good Q. We want a Q that works for us, basically. That's not too close to P, and we want to minimize. It says we want this to be 2. Minimize the multiples for this stuff. We want it be really hard to have any chance of any kind of hacker, cracker, whatnot, mathematician factoring out P times Q. And that's what we're going to do right here. We're just going to keep going over. One of the things that I like to do is, like, if I do a 100-digit prime for P, I'll do a 101-digit prime for Q, and that will certainly help us out with this little thing that says that there's a what does it say here? You need to be greater distance than this function here, distance apart, to avoid factorization from the Fermat factorization possibility. If it's 100 digits and 101 digits on your prime, you don't have to worry about it. So, but if it's like 100 digits and 100 digits, there might be a chance it's within that neighborhood that they can figure out that P and Q are close to each other. Take the square root of the PQ and just start going up and down and finding it. So we're just going to loop through that until we find one where the absolute value of P to Q is greater than this value here. I know that was a little fast. And we break out. Not that big of a calculation, really. And if it comes up as 1, if Q comes up as a 1, if I fail that, it's a fail and returns meh. It's like, meh, you're bad. The next thing we're going to do is find our E function. Well, we're going to get that key, so we're going to call that generate key function that was over here in the math module, and we're going to come over and look at the values that come out of it. Now remember, when we generate these keys, I'm asking the default at the lower limit E to be true, so I don't call out the limit I want here, but it's going to know to give us a big E that comes back. So the other caveat is here, is the D big enough to, the D value big enough to pass muster. And Michael Wiener, J. Wiener here says, if E is less than this formula here, which is, P times Q to the 4th root divided by 3, it's easy to factor. So we're just going to go through, and I have to step through some stuff because these are pretty big numbers that we're dealing with. So just take this function, this formula here, and do it in parts, and say if D is greater than the limit, and if E doesn't, there's a chance that D and E could be equal to each other. That'd be really weird, but then break. We found it. We can go. And I guess I've got that guy right there just to see how many counts I did. So I'll just get rid of that for right now. Boom. You don't need that. And then I'm going to put P and Q onto the payload. And there we have P and Q in the payload, and we have also D and E. So it goes off and says, this is the last check. It says, hey, if D is less than 1, or if E is less than 1, which I think the inverse will turn a -1 if it's bad, or if they equal, nope, no bueno. You don't pass go. Don't get you $200. Don't get to collect your $200. If not, you're going to update our keys, and then we're going to calculate our key bits, which is just a number of bits in the int of P times Q. And then we're simply going to turn P to Q into a string, and then get the length of that string and call it, that's how long it is. And then take our payload, which is our actual key part of it, and then return that result. This next function is just going to generate a list of keys. I'm going to give it a number of how many keys I want to generate, and a range of prime numbers, 100-digit number here, maybe 200 here, and just regurgitate that through a loop. That's nothing much to this function here. It's just a helper function. So let's just go with this. At this point, we'll just walk through one step at a time. I'm going to save selection because apparently, I did. What did I do? I deleted a couple lines. So the first P length we're going to get is 10, and I'm going to call the get key P length 10, P length 10. So I'm sending two 10-digit numbers through, and so you can see, well, let's just go, boom. So it went through, and it returned exactly what we wanted it to really quickly. I got my return code true, that's good. I don't have anything in these guys listed here, but my payload should show me the P and the Q, the number of digits, so it's 20, right, and 65-bit key, or 65-bit PQ, E, D, and I didn't fill out the start time. Of course, this represents the entire key, so you don't want to necessarily give that to anybody unless you like having things figured out or cracked for you, but we'll throw away the P and the Q and the D for the public, and keep all the good bits a little later. Next, we're just going to walk through the generate key list. We're going to generate 10 keys of 300 and 301 digits. Well, I'll just walk through this one so it sees the whole thing. Step in, and here we're going through it. It's generating a new key right now. It's got the key, get a new key. Is that the one I did up here? Get new key? Yeah, get new key. So I'm just going to put a breakpoint there, and we'll catch it on the next one. I'll step into there. So we've described this function, maybe not so well. Mostly this is for me, so I can figure out and remember what I was doing. The payload, got the prime wrapper function, got a P value coming over here. This is going to take the longest time, the P in the Q. So the P is literally that number right there. That's your first prime number. And your Q, your first attempt to Q, again, I picked a 300, was it 301, is that number right there. I'm going to say, while the greatest common divisor isn't 2, do 1. So apparently, you know, the greatest common divisor between those two, P and Q, weren't, so it's going to do it again. And this is what slows it down. We want to make sure we get P and Q that are good. So it's not above max attempts, so I'll go back to the top. Another one, so this is going to count up by 1. Right, come on, what number you? I said, well, I need to fix that. That's clearly a bug. So this is gonna get one by hook or by crook. So if I click right there, that's just a little bug we'll fix in a second. It should come out here, and eventually, unless I really screwed something up, which is totally possible. And there, it found one. I don't know how many iterations it went through, excuse me, to get it. This is the requirement. We want to have our prime numbers be as hard to factor as possible. Step over that. P doesn't equal Q, go. Count plus 1. Now we're going to see if it's over the value. It will be, because we did, what, 300 and 301. Now if Q equals 1, it doesn't. We're going to keep going. Well, count. Now we're going to go find our E and D values. So we got an E at this point. Right, if we come over to the debug console and say keys, let's just type it. See, so we can see P, Q. Let's go keys E. That's to spell it right. And P's D. So those are our first two candidates. We want to see if those will work for us. And if it does, it'll break out there. And it broke from the loop, so we're good. We can use this key for real, in real life. And we're going to check one last time. Okay, it's not. We're going to return back that result and go through this function module one more time. And it should pop up down here. So I will just put a breakpoint there. Do I want there? Yeah, fine. And click there. And we just wait for in this case, the 10 keys to generate with the breakpoints that are going on. And there it popped into out of that guy. So let's just print them off. Click the wheel over here. Just print them off one at a time and just go, I guess. Click, go. And there we have the keys. So we've, let's click done. Fine. So we've printed off a simple key there, then we made bigger keys. We told it to generate 10 different keys of 300-digit lengths, and you can see here, interesting bits, there's P, there's Q, and then you have the digit lengths, and of course, since we're trying to find prime numbers, they're not always easy to find, so sometimes you have to do multiple tries to get the right set of them, so sometimes the digit lengths are a little bit bigger, and sometimes a little bit smaller, I guess, and then your key bits. So that's pretty much it for generating the keys. The next one will be actual encryption.